We're going to move farther from the pavement and look at slopes and ditches. Ideally, roadside safety would be substantially improved if wide, flat areas were provided alongside the roadway. Ditches would be located far from the edge of the pavement, and cut slopes would be flattened to provide recovery distance for a vehicle that left the travel lane. The driver wouldn't have to worry about running into anything or flipping over. He'd have plenty of room to regain control if he ran off the road. Practicality, however, limits the regions where this is possible. In some areas of Florida where the terrain is generally flat, roadside slopes can easily be graded to a safe shape, but in many places this is not the case. The critical areas of roadside slopes and ditches are the distance of the hinge point from the edge of the roadway, the steepness of the front slope, the toe of the front slope, the shape of the ditch itself, and the steepness of the back slope. To understand how each of these elements affects safety, it is important to know what happens to a vehicle when it crosses each area, that is, when it crosses the hinge, the slopes, and the ditch itself. When a vehicle travels over the hinge point, two things can happen. It can become airborne with all wheels leaving the ground and it can hit something coming down, or it can roll over on its side or end over end. It may be easy on the stuntman on Dukes of Hazzard to roll a vehicle, but it's hard on you and me. Many slopes alongside the roadway are of about 10-to-1 steepness between the travel lane and the hinge point. A vehicle will become airborne at about 40 miles per hour as it crosses the hinge point when the front slope is steeper than 6-to-1. If a vehicle becomes airborne, the driver has no steering capability at all. Rounding the hinge point will greatly reduce the tendency of a vehicle to become airborne and thus will increase the chances of the driver to maintain steering control. We don't round the hinge point on purpose in Florida, but sometimes nature does it for us, which is fine. Now let's move down to the front slope. The steepness and condition of the front slope affect what happens to a vehicle once it gets beyond the hinge point. Three things can happen. The vehicle can roll over sideways or end over end when it lands on the front slope, or it may skip sideways or in a circular motion as it travels down the slope. Or the vehicle may not be able to stop or return to the roadway before traveling all the way to the bottom of the slope. Can you imagine traveling to the bottom of this slope? This front slope is roughly 3.5-to-1. We can see that this vehicle going off the pavement at 60 miles per hour loses control and in this case traveled 145 feet after leaving the pavement. The impact caused the tie rod to break. Obviously, even 100 feet of clear zone would not be sufficient space to recover in these circumstances. These roadside tests indicated that rollover is not expected to occur on slopes flatter than 3-to-1 at 60 miles per hour unless the slope surface is severely rutted or looks like this. However, a vehicle going 60 miles per hour cannot be turned back toward the road on a 3-to-1 slope. Instead, it will slide out of control in a circular motion. As we just saw, on slopes steeper than 4-to-1, the vehicle will travel to the bottom before steering recovery or stopping can be attained. We can change the situation dramatically by failing to maintain or repair the slope. Severely rutted slopes, such as this to say the least, can cause vehicle rollover or other unexpected maneuvers like complete loss of control. Impact severity or dig-in force is influenced by the steepness of the front and back slopes that form the ditch region and by the cross-section of the ditch itself. The steeper the front and back slopes, the greater the impact on the vehicle. That back slope is really critical. It is what brings the vehicle to a sudden stop. This accident involved a guardrail, but most of the damage resulted from the tractor hitting the back slope. This is an example of how the back slope increases the severity of an accident. Unfortunately, there's nothing maintenance can do to change this back slope. Next, we'll look at the ditch itself. There are 4 basic ditch shapes that are used. The flat-bottom ditch shapes are safest, particularly if they're wider than 8 feet. They are the types we use in Florida. Remember, the farther we can separate the front and back slopes, the better off we are. Even though we go to a lot of trouble trying to round the ditches, rounding the corners of a flat-bottom ditch does not increase safety. So what we're saying is rounded is worst, flat bottom is best. Now let's look at some maintenance points. Maintaining a smooth, stable slope surface is a definite safety improvement if the slope is not shielded by a guardrail. If regrading is not possible, guardrail should be considered on slopes steeper than 3:1, particularly if the toe of the slope is hazardous. Obviously, it is safest if we maintain as wide a clear zone as possible. Slopes should be routinely inspected and repairs programmed for regrading, mulching, reseeding, and erosion control. Using proper procedures will greatly reduce the need for doing the same type of repair over again. Many roadside problems can be improved by slope grading activities. With the increasing installation and maintenance costs of guardrails, it is becoming more and more cost-effective to regrade slopes to eliminate the need for guardrails. Let's look at some examples. Here we have a fairly good ditch with a flat bottom. It is very rideable. We only need to worry about erosion. Regrading can do a lot to increase safety. This is a basically good slope, but the two deep pockets destroy its safeness. Obviously, if a vehicle traveling along the road were to go off and hit one of the pockets, the driver would be in trouble. Regrading, along with removal of the ineffective short section of guardrail, would also be an improvement. Regrading this infield of an interchange would greatly improve its rideability. Here we see a median regrading project which eliminated about 1,000 feet of guardrail on each side of the highway. It was part of a removal project in which more than 50,000 linear feet of guardrail were removed. Taking out unnecessary guardrail probably represents one of the most cost-effective safety treatments for slopes. This slope is very rideable. The barrier could be removed to provide a smooth surface. Here's another section where a substantial amount of guardrail could be removed. The guardrail is expensive, and the slope here is safer than the guardrail is. Remember, slope dressing serves several functions. It not only maintains the slope surface, thereby creating a more rideable slope, it also reduces ditch cleanout problems, which we'll talk more about in just a minute. In addition, it protects the pavement by reducing water seepage under the pavement edge. Modifying the roadside and ditch area to achieve a safer roadside can be accomplished in the same operation. Ditches need to be cleaned on a regular basis to keep the drainage working properly. Vegetation, silt, and debris can undo the drainage function, resulting in ditches becoming ponds or even flooding the roadway, thus creating a hazardous situation. Standing water in ditches is an indicator that the ditch may need cleaning. When we're maintaining ditches, we have to be sure we don't create hazards. This is a case of overkill. The ditch was dug too deeply. Providing the ditch has the right safety shape to begin with, ditch operation should restore the ditch to the original design. Here the operator provided too steep a front and back slope. Remember, it's important to maintain the back slope as flat as field conditions permit. It's also important to be aware of the vertical curve of the roadway when cleaning ditches. At the top of a grade, the ditch may be more gently sloped. Paved ditches also may need cleaning, either with a grade awl, by hand, or with herbicides. Well-maintained ditches not only function well and are safer, they also promote good public relations with property owners along the roadside. Besides the shape of the roadside itself, we have to watch for other hazards. The primary problems found alongside the roadway include sign supports, luminaire supports, curbs, and drainage structures. We can have a perfectly formed but totally unsafe ditch because of the hazards in it. Here this 2-to-1 slope becomes even more hazardous because of the exposed drainage structure. We'll look at drainage structures in more detail a little later. We also have a problem with trees and plants. Unfortunately, safety is sometimes at odds with beautification goals. Although there is continued pressure to leave as many trees as possible on the sides of highways, it must be recognized that a tree can produce a serious accident when a vehicle collides with it. Trees located close to the roadway edge create not only a safety hazard, but a continuing maintenance problem as well. Trees and ground cover bushes planted to improve slope stability will require trimming or possible removal at a later date. Small trees, which are not particular problems when they're planted, grow to become large trees, thus becoming large hazards. As a general rule, trees should be planted only at roadside locations where there is a low probability of a vehicle reaching them after leaving the roadway. Here the front slope to the ditch has been well cleared. The trees are left up on the back slope where there's less chance of a vehicle running into them. We also have to be careful to look for and remove trees that grow up from airborne seeds, as was the case here. One other problem area, as can be seen here, is raised surfaces in the side slope area. We sometimes have driveways and freeway median crossovers like this to contend with. Anytime a 4-to-1 slope berm is encountered, maintenance should schedule a fill and regrade to a 6-to-1 slope. 4-to-1 slopes are okay when vehicles are going 40 miles per hour, as we just saw, but look out when they're going 60 miles per hour. So we have to safely maintain the slopes and ditches and watch for poor placement of rigid obstacles. Okay, let's look more closely at drainage structures. As you know, drainage structures are primarily used to collect water and to provide the path to off-road drainage facilities. Functionally, drainage structures should have sufficient water carrying capacity so that overflow or water backup does not occur. Also, they should create minimum hazards to vehicles which might hit them or travel across them. A third functional requirement of drainage structures is that they be as maintenance-free as possible. Openings clogged with debris greatly reduce the water carrying efficiency and add to maintenance headaches. As we just said, the primary function of a drainage structure is to adequately carry water away from the roadway. We must be concerned about this and about safety. Placement of the structure, design of the openings and grates, the spillway condition, and other factors affect both the hydraulic efficiency and safety qualities. Many times an improvement for safety causes problems with the water flow efficiency and vice versa. So we have to reach a happy medium somehow. There are two basic types of drainage structures, drop inlets and culverts. Drop inlets are those devices which collect water and direct its flow to other channels of flow. There are 4 general types of drop inlets: flush inlets, raised inlets, depressed inlets, and curb inlets. Flush inlets like the one shown here are designed to fit smoothly with the terrain or other highway features such as a curb or deck structure so that vehicle wheels will not snag when crossing the inlet surface. Raised inlets include those which have parts above the immediate area around them. They create a rigid obstacle that a vehicle wheel can impact. This tabletop inlet is a rather severe rigid obstacle for a vehicle because it projects more than 6 inches above the surrounding ground surface. This is a modified design which is less hazardous than the one we just saw, but even it is not acceptable from a safety standpoint. Depressed inlets are those where the inlet is below the ground level, or they may be set back into a recess in other structures such as a bridge wall or a concrete barrier. The 4th type of drop inlet is the curb inlet. Curb inlets are generally constructed in conjunction with gutters or in the face of a vertical barrier. The opening is parallel with the traffic lane. This guardrail, by the way, should be flush with the curb. This inlet illustrates the parts which contribute to proper function and safety. The collector basin in this inlet has been lined with concrete to provide an erosion-free area. The opening contains a grate to prevent wheel snagging. The surface has been graded and lined to conform with the surrounding ground surface for vehicles to pass over them safely. While inlets basically collect water, culverts carry water under the roadway lanes or under structures to direct the flow to ditches alongside the roadway. They vary in size from small diameter pipes to large box culverts which approach the size of bridges. Culverts crossing under the main lanes are transverse culverts as we see here. The safety hazard is the steep drop-off into the spillway. If you run off the road here, that's an awfully large area to fall into. Because of the severity of the hazard here, installation of guardrail as specified by our standards for median hazards would improve the situation. Longitudinal culverts run parallel with the main lanes. They carry water under structures or under intersecting roadways. Most of these are under driveways. They create even more of a safety hazard because the vehicle can impact directly into the open end of the culvert. This transverse culvert illustrates the parts that affect safety. The head wall and wing walls are rigid objects that can be hit. The opening is not graded. Thus, a vehicle leaving the main lanes could be severely damaged dropping into the concrete-lined spillway. Safety, hydraulic performance, and maintenance needs can be improved by activities ranging from merely cleaning debris from the opening to total redesign and construction of a new structure. We'll look at several factors affecting performance next. Just as is true of any obstacle in the roadway, the farther the drainage structure is from the travel lanes, the less likely it is to be hit by a vehicle. Therefore, during new installations or combined with other roadside safety projects, placing an inlet or culvert at the outer edge of the clear zone is a substantial safety improvement. When major reconstruction projects are undertaken, the new structure should be designed to be as safe as possible. Often, culverts or pipes can be connected together, eliminating two exposed ends. Here's an example of two culvert openings that need connecting. In many cases, it's necessary and advantageous to relocate ditch lines as well. Locating this culvert opening out of the clear zone is a safety improvement. However, the end opening here is just as bad as it was at its former location. There's still a deep drop-off area into which a vehicle can fall. Using a lower head wall or extending the pipe beyond the retaining head wall and grading the slope would improve the safety aspects and make it easier to get across. The low underclearances of modern vehicles make it important that inlets be not more than 4 inches above or below the ground surface. The drop-off at the opening of a transverse culvert creates a severe hazard to a vehicle. The deep hole around many large-diameter pipe or box culverts must be shielded by barriers unless the opening can be extended outward. The safety of this particular opening would be greatly improved by construction of a deck between the culvert head walls using a flush inlet. Note that the guardrail here does not adequately shield the hazard. Here, the longitudinal graded culvert was formed to the crossroad incline. However, the high blunt end of the culvert section produces a hazardous situation for vehicles approaching the median. Although some taper of the concrete is possible, the opening has to remain for hydraulic purposes. A different type culvert is needed to make this safer. If the pipe opening is small enough and flush with the slope, a grate may not be necessary. Here we see what happens when a vehicle crosses a 30-inch wide culvert opening which has been fitted to a 5-to-1 side slope. The car is going at low speed. Slow speeds are more hazardous than fast speeds for crossing culverts. The car hits the culvert at a sharp angle. As you can see, the car experiences no real problems. This much opening here is expensive, however. Improving the traversability of the culvert opening solves only part of the safety problem. The terrain around and beyond the culvert should be graded to allow recovery room for a vehicle. A vehicle would safely cross this grate only to become trapped in the abrupt pocket between the roadside and the back slope beyond it. Another safety and maintenance problem is created by debris at structure openings. It is important to maintain a clear spillway area. Debris accumulated around the structure opening reduces water flow, causes erosion, and can also cause a vehicle to lose rideability. Vegetation and accumulated debris, sticks, mud, etc., increase the accumulation of more debris, which further reduces water flow efficiency. Debris changes the intended flow path and causes erosion around the structure. Keeping vegetation mowed or chemically controlled also helps reduce the problem, but we still need to periodically clean debris. A sewer cleaner can be used to clean culverts. Water jets force debris out the culvert and down the ditch, or a suction hose can be used to suck the debris into a truck. Cleaning a 40-foot, 18-inch wide pipe takes about 20 minutes and uses about 500 gallons of water. If the same culvert were cleaned using only a long-handled shovel, it would take half a day to clean. Using grates with open bar spacing helps to reduce the debris problem. Also, lining the spillway will increase the water flow speed, which will carry debris beyond the end of the opening. Here we see a 30-inch spacing on a grate for a culvert flush with the side slope. By the way, the 1-foot section for the lower end treatment on the grate is somewhat hazardous, but is necessary for water flow. This Honda is going across the culvert at 30 miles per hour and is hitting it on a right angle. From the close-up, you can see that there's a lot of action in the rear axle, but otherwise the car got across the grate without too much trouble. A larger car going 20 miles per hour experiences some tire flattening going over the same graded culvert, but again, there were no real problems. This time, the vehicle was programmed to try to steer back up the slope to see if there would be any problems in trying to recover, and there were not. The important things to remember about grates are the grate should not restrict the flow of water, it should not be a debris catcher, and finally, we're trying to eliminate, not create, a hazard. Safety improvements to culvert head walls may involve rather extensive structural modification. Many problems can be identified during routine maintenance activities and scheduled for later improvements. The improvement should be coordinated with the responsible agency or department. When you inspect a culvert, these are the things you should think about to improve safety. Is removal or relocation possible? Is a barrier needed? Does an existing guardrail properly shield the culvert? Are hazard markers and delineators needed? Here we see an acceptable culvert head wall. This is a sandbag inlet, which is acceptable, but perhaps not in the manner in which it was installed. A more gentle slope would have been safer. Look at this culvert closely. We're going to ask the following questions as we inspect it for safety. These are the questions you should ask yourself as you inspect structure openings. Is the opening flush with the slope? Yes, the opening appears to be flush. Is there erosion? Nope, there's no evidence of erosion. Is the incline flat enough? Yes, it appears to be fine. Has debris accumulated? Yes, here's the problem. Vegetation and debris have accumulated. What's the safety significance of this? It may clog the culvert so water may run up on the road. Many of the factors which reduce the performance of grates on inlets and culverts can be identified during routine maintenance. Some can be corrected easily by maintenance. Those that would require design changes or substantial reconstruction can be identified and programmed for future safety improvement projects. At least these points should be checked when inspecting grates themselves. Is a grate needed? No, in this case it's there. Are there broken bars? Yes, it's a definite problem here. How is the grate anchored? It appears it's anchored properly. Can a vehicle safely cross over it?